All right. Our presenter, we're going to go ahead and get started with our presentation. Our presenter today is Greg Shanos. Greg, sorry if I'm mispronouncing your last
Yeah,
name.
that's correct, Shanos.
Okay. Greg is a NASA JPL. Well, you guys all know Greg. He's been on here enough. NASA JPL
Yeah.
Solar System Ambassador. This is part two of Greg's Mars 2022 Observer's Guide presentation. Back in October, he did the visual observation presentation. This is the planetary imaging part. So I guess I'll stop talking and let Greg go ahead. I'm going to stop sharing. And Greg, it's all yours.
Okay. Share my screen a sec. Let's see. Share screen. Okay, can all see that?
Yep.
Indeed. Yes.
All right, good. So this is a rather lengthy presentation, and since most of this is the same, the beginning part, I'm going to skip through it because I gave it to the Southern Vermont Astronomical Society and the Southern Vermont Astronomical Society, so and it was over an hour and a half. So being Christmas, I'll just, this part is all the same. And I want to, this is important, is to know the kind of the anatomy of Mars. These are what I call the albedo features. So red is the color of iron oxide rich dust. So this is the desert parts here that are orangey red. Dark gray is the color of volcanic rock. Okay, and white is the color of ice, with this, which is carbon dioxide with some water in there. Okay, so it's basically dry ice, CO2. Okay, and these have all proper names here. And this is oriented north, south, east, and west. And this is one of my favorite features called Certus Major. And I kind of give kind of whimsical shapes to these things. This kind of looks like the continent of India if you were to turn it right side up, see? And then this is Sinus Sabius and Sinus Meridiani. And then this, to me, looks like a cobra. See how it's lying like this with its head here? So this, to me, kind of looks like a cobra. Can everyone kind of see a cobra there?
Mm-hmm.
And then this is the Hellas Basin, which is round. And then this is Olympus Mons, which is the largest volcano in the solar system. And this is over twice the height of Mount Everest. And the base here is like the size of Arizona, state of Arizona. It is huge. And what's amazing is you can actually image it with an 8 to 10-inch scope in your backyard. And I'll talk about that. That's what we'll talk about today. So we need to familiarize these features here. Now, this is oriented south as up. And the reason for this is back ALPO, the Association of Lunar and Planetary Observers, people were using reflectors back in the day, and reflectors invert the image, so south is up. So people that were submitting and sketching back then, we didn't have video and photographic technology. They were sketching this. They always sketched it with south up, so that's the way everyone's used to seeing it. But now we're submitting our images to NASA and to other professional organizations, and they want to see it north, south, east, and west. They want to see it oriented that way. And when I do my images, I orient it this way, okay? But when you look at Certus Major now, it looks like India, because see, it looks like the continent of India. So this is, and then this is located here in, I can't see because this is in the way. There it is. So, so here it's about 290 degrees. So the central meridian's important. That's right here through the center. All right, so at 3:15, this is what you're going to see. So this is Eden, Moab, Arabia area. That's this area right here. These are Hubble images from 2003 when it was super close. Sinus Sabia, Sinus Meridiani, that's here. This is our cobra, what I call our cobra, and then Margarifera sinus and Aurora sinus. And I think of Aurora sinus as having like fingers. See these things going down here, they look like fingers to me. And then Solus Lacus is the eye of Mars. And doesn't that look like an eye? It's a pupil here. And then, I mean, there's the pupil and then there's the eye. Isn't that cool? Really does look like an eye. So that's what it's called, the eye of Mars. And then Mare Serenium, Mare Cimmerium, and Mare Terrenium. And then here's where Olympus Mons is located. And this is the Tharsis region, it's called. Okay, and then this Mariastanium and Nilacus Lacus. This reminds me of Devil's Tower in Utah, where they filmed Close Encounters of the Third Kind, doesn't it? So use your imagination a little bit, because that helps me kind of remember this stuff. And then these are images that amateurs have taken. Damian Peach, Chris Go, and Anthony Wesley. These guys are semi-professional imagers. They've been doing it for a long time, and their images are tops. And notice how you can really see a lot of these features. So this is south up, so this is oriented the same here. So at 297, which is right here, you're seeing all this area. Okay, so that's the importance of the central meridian. At 29, which is right here, you're seeing all of this. Margarifera sinus, Aurora sinus, Mariastania, see here, and then Solus Lacus 109. Right here, you got Solus Lacus. See, so you can kind of get an idea how to read this map. This reminds me of kind of a snake. Mare Serenium and Mare Cimmerium, and here's the head of the snake. If you don't like snakes, think of a worm. But we already have a snake right here, a cobra. So think of this as a worm or another snake. And then look, here's Olympus Mons, imaged by an amateur astronomer. That's this right here from the Hubble, and here it is. Isn't that amazing? So you can really see a lot of detail on Mars and all the other planets. And I'll talk about how to make images like this. How to obtain images like this is really, really easy and very inexpensive. Okay, and then you can have global dust storms. A lot of this dust will lift up here and totally encircle the planet. In the 2018 apparition, there was a global dust storm, and I imaged it. You could see here. Notice you can barely see the cobra here, Sinus Sabius and Sinus Meridiani, see? So it really obscures everything. Well, this year we're not having any global storms, which is a good thing. And then what ends up happening is Mars always changes its appearance. The size of the polar region varies. The South Pole right here grows in the winter and gets smaller in the summer. Clouds appear white. You can get clouds. Here's here's a cloud right here. You identified it. See, but you look at the rest of this here, it's reddish orange, and here you get a nice white cloud. This is the South Polar Cap. So, and notice how it's shrinking. See, it's a lot larger here than it is here on that image. See, so you can clouds appear white, dust storms appear reddish. Okay, and what'll happen is these albedo features will appear darker or lighter depending on the dust. If there's a lot of dust in the atmosphere, these will appear lighter. There has been a lot of dust on Mars, not localized, but it's spreading through the atmosphere. So these albedo features are not as dark as they were during the 2020 apparition, but it's nowhere near this, which is a good thing. Okay, and you don't have to talk about telescopes. I mentioned this, the orientation. If you're gonna look at it visually, two filters, all right? You should get the the 25, the 29 red, which is a dark red. This basically will show everything all these other filters show. And get this 47 violet, which is a deep violet, and this will show clouds. So if you're ever unsure if you have clouds, just throw on a 47 violet filter and the cloud shows up really white. So it's very diagnostic. And that's if you're imaging too. So, okay, this is phenomena called blue clearing on Mars. And what this is when you look at it through a violet or blue filter, a lot of these albedo features seem to disappear. And originally it was thought that there was something happening in the Martian atmosphere that it would absorb or scatter shorter wavelengths. And then Mariner 6 and 7 orbiting Mars took photos in 69 and it didn't diminish at all. And then Carl Sagan, 67, presented evidence of these blue clearings in the atmosphere of Earth rather than Mars. And what happens is if blue clearing is occurring, this will look a lot more like this. It will look just like the color image. And these usually occur when Mars is closest to the Earth, largest in angular diameter, highest in the sky, and therefore you have increased contrast of surface features. Could also be the phase angle, the way the angle is of the sun, Earth, and Mars. Okay. All right. So, all right, good. Now we'll get to the astrophotography part. Okay, the past. How many people remember this? Remember?
I had one.
Huh?
I had that exact same adapter.
Yeah. That was the Meade, or Teleview may have had one. Celestron, right? Yeah. What you did is you had this telextender and you used fast film 400 or 800 ASA. I remember when Halley's Comet came out in 85, 86, 1600 film just came out. And I thought, wow, how can anything get better than this? And use the cable release. I couldn't find a picture with a cable release, but it attaches where you'd snap the picture so you're not actually touching it. And then you have mirror slap, these things which like that, so it would vibrate, and this caused significant vibration and would blur it. You're limited to 36 pictures or slides. I usually took slides, and you were lucky to obtain one decent photo, decent blurry that wasn't, that was just, this was just, that's why most people back in the day during print film sketched the planets, because you didn't really get much out of film. You were lucky to get anything. So, but now we're in the digital age, and this is how it all began for me. There was actually an occultation, a grazing occultation of Mars in Florida, July 17, 2003. And this was over here near Lake Placid and Sebring. And here's the coordinates, okay? And I remember this was on kind of Monday or Tuesday. It was on a work day and I couldn't get out of work. I was able, this happened around 3 a.m. or so. So I was able to just pack it up after and go to work and then change. And then the funny thing here is my camcorder died out that day. So I brought an 8-inch Schmidt Cassegrain. I had adapters, so I was going to videotape the whole thing. And it died on me. It was like this. And then I saw Dr. Don Parker here. And Dr. Parker's he passed away in 2015, unfortunately. And he was very funny. He said, I pass gas for a living. He was an anesthesiologist. Get it? Yes. Like farting, so it's just hysterical. So he was very humorous. And I saw him with this little 8-inch, reflector, and he had this webcam. And he had the webcam connected here to his van to a laptop computer. And this is what I was seeing on the screen. And I was blown away. I'm like, what is this? This is as revolutionary as as Galileo turning the telescope to the heavens and seeing the moons of Jupiter and the craters on the moon and stuff like that. And Galileo didn't invent the telescope. A lot of people think that it was already invented. He was just the first to turn it up to the sky and actually, like a good scientist, record what he saw, and it was just amazing. And so Dr. Parker told me, okay, you got to get a 2U webcam, and then K3CCD Tools is a software. And then once I got home that night, first thing I went on Amazon and bought this stuff. And oh man, I was just so excited. I couldn't believe this. And this is what we saw at the time. It was grazing. It never actually went into the moon, reappeared, and disappeared. Actually went along the side. Isn't that cool? Just like this. This is what you saw. You saw it go right across the side of it and then leave. Isn't that cool? It's called a grid. That's really rare. You need to be in the exact position, And it was hard to find this place because this was before we had a GPS and stuff in 2003. GPS was very expensive, so I didn't have. I had this, but I didn't have one of those map. I had MapQuest. Do it out, but I didn't have the real time like on cell phones. But either way, this was how it all began for me. And then,
Greg, I think I have a question.
Sure.
I was just going to throw in a comment. I'm in the New Haven Astronomical Society, and there were people there who talked about parts of northwestern Connecticut to see that grazing. And, they had a certain area where they had picked out, and they use stellarium actually. And,
right.
Putting in your, you could use stellarium, I guess. And
I
just wanted to throw that out as a way to maybe help find those spots.
Stellarium didn't exist in 2003. It was still the beginning of the digital age. So,
there was a posting on Sky and Telescope that showed where the grazing and the full occultation occurred, and it just clipped the northwest corner of Connecticut and went way above Springfield, Massachusetts, and just the lower edge of Vermont. There was probably 100-mile wide swath before you got a grazing and an occultation or nothing. But
so
as Greg is talking about historically, 2003, we didn't have those kind of tools.
Yeah. But you can do all this on Stellarium. It'll tell you exactly where to go and everything. But then this was just exciting. And then this was the Orion had this digital eyepiece which I bought. This was crappy. This was not as nice as the webcams. And then this is the Meade and Celestron webcam here. And but these were better than all of this with Philips 2U cam, okay? And Philips, is a great company. They make high-end electronics and stuff. So this was the 2U cam 2. He had the original 2U cam here. And then what's great about this is what you did essentially is you took a 60-second video, all right, through the webcam, and then you align and stack the images. And I'll talk about that later. And these all worked on, remember, Windows XP. That's what we had in 2003. XP was a great program, you have to admit. And then, but the thing is, they only work for bright planets, okay? And the moon and the sun and the planets. You don't need any dark frames or flat frames and all that stuff you need in deep sky astrophotography. The limitations of the webcams where you had slow frame rate, noisy images. Remember the webcams, you had this, like almost like a stop motion kind of thing, right? Remember? Like here now you can see it in real time, but back then, you had kind of, remember that? And so that kind of limited you, and the images were very noisy. They weren't clean at all. The images here that I'm seeing everyone now are nice and clean. And an eyepiece adapter is required to mount the webcam to the telescope, and that's what the eyepiece adapter looks like. What you do is you unscrew this so you don't have a lens to it, and then you put that eyepiece adapter in. And then the upgrade to this was this SPC 900C, and these were all CCD chips, and they had audio too. So you spoke what the time was and all that stuff, so that you had a reference point that was important scientifically. And then this was the program K3 CCD tools, and it's still available online. I think you have to buy it maybe, but it's worthless. There's much better programs out now that I'll show you, but the webcam days are gone. Now here's today's video cameras. The two that are the best here are I'm not familiar with a lot of these other ones, but the QHY CCD is used by a lot of people. The ZWO, this is what I use. I originally started after I graduated from the webcams. I went with the imaging source, which is very good. And the imaging source actually makes the next star for Celestron. And the imaging source, I was surprised to find, used the same CCD chip as the SPC 900C. The big difference was the electronics. It didn't have the stop motion as much, and it was the noise went down, but the CCD was exactly the same. So they were able to actually make it much faster frame rate and less noise. And there's one other one that's not listed here called Player One that's starting to make a dent in the whole imaging thing. But now most cameras are CMOS now. CCD is becoming extinct. When CMOS first came out, it was not very good in the dark. It didn't see very well in the dark. And now all security cameras, they all use CMOS. Nikon, Canon, all of those use CMOS. Everything uses CMOS. Now, the only thing you would use CCD is maybe some high level thing like the James Webb telescope or something like that, but for commercial use, it's all CMOS now, which works just great. Even for deep sky astrophotography, you can't find a CCD deep sky astrophotography camera anymore. And the thing is, the CMOS is much cheaper to produce, so they can get larger. They can get 16 megapixel size chips in a CMOS and larger, whereas with CCD, you were lucky to get 2 megapixel. I paid $1,000 for this with a 2 megapixel monochrome chip. Now these are going for 300. And if they're on sale, 250, and you can get some older models for 150. So these are really, really inexpensive, these cameras now. So they're not going to break the bank like Deep Sky does. Okay, so what you would need is a telescope with microfocuser that's tracking the planet, a laptop notebook running Windows. Some of these programs, they're starting to get better with Mac, but not all of them. So you'd have to use Windows. Use Stellarium. I like using the Sky because I started out with the Sky 6 and I got the Sky 10. But I'm starting to use Stellarium more. It's an incredible, it's absolutely free, stellarium.org. Just Google that. And they just upgraded the 1.1. So it's even more bells and whistles. So, and then a CMOS camera, and then Fire Capture or Sharp Cap. These are the two programs to actually capture the video. You capture an AVI video or what they call SCR video. Auto Stacker, this aligns and stacks the video. Registack 6 sharpens the final aligned and stacked image. And then Astra Image and Photoshop are equivalent for final processing. So all of these are free. Stellarium is free, WinJupos is free, Fire Capture is free, Sharp Cap, there's a free version and a professional version that you have to pay for. AutoStacker, it's free, Registax is free, and then this one's only $42 and Photoshop's expensive. But Photoshop Elements has the same stuff, so you can get that for $100 or a couple $100 and use that. And then a windshield is recommended because what happens is you're imaging and then you get a gust of wind and it just blows the image all over the place. But there's a workaround that, which I'll mention. So if you can get a windshield, be good. So here's my setup here. This is my equipment. I have a smaller telescope, a 10-inch. 8-inch is the minimum you could go. 10 and up is recommended. A lot of people, those that I showed before, were taken with 14-inch scopes. The catadioptric is the preferred telescope to use because you're going right through the center of the scope. So you don't have any field rotation effects because you're looking at it under very high power. So you don't need the new HD or the advanced coma-free versions. This is a classic Cassegrain here. And do not use the star diagonal. I was informed by Dr. Roger Venable from Alpo. He's the Mars coordinator, not to use one. And oh my God, it makes such a difference because if you have a diagonal prism up here, this is what a diagonal prism is right here, this thing right here. And here's the microfocuser, okay? So don't use this and put it directly into it much sharper because the mirror there is not meant for like astrophotography. It's more for visual. But there's a little caveat here and a little problem. If you don't screw this on tight and this is pointed higher, this will just slide right out into the cement. And it's happened to me more times than I can count. But these cameras are indestructible. There's no moving parts. So they fall out. I'm like, ah. Yeah, I pick it up, put it back, and it's working just fine. I don't have to reset it or anything. So these things are pretty indestructible. And then I have 4 cameras now, and I'll mention that later. You need a UV IR blocking filter, cut filter, because the chips are very sensitive to the infrared and a little bit to the ultraviolet. And if you don't block the infrared, what happens is you don't get as sharp an image because the longer wavelengths tend to, you don't get as sharp an image on the albedo feature. So make sure you put a UV-IR cut. Use a Barlow lens, okay? And then I have this computer. I use an MSI, which is actually a gaming computer. And truth be told, I have no idea how to play a game on it. I've never played a game on it. I use it because it has 6 cores and 12 threads, and I upgraded it to Windows 11, and I added a 32 gig card, and I have 40 gigs of RAM in it. So it's a nice fast computer, and you need RAM, and you need more cores in there to get the speed, you know. And one great thing about this computer, see how these keys are red? This model, the GF65, the keys come red. And I looked up on YouTube, you can change the color of the keys to different colors, but this is the default color for this model. And this is perfect red. And when I put a red shield on here, it's perfectly all red. It doesn't ruin your dark adaptive vision. It's just absolutely perfect for astronomy. And I nicknamed it Missy, M-I-S-I. I just add an I there. So I say, I'm out at night with my telescope and my Missy, observing the stars. Well, the wife watches TV. So I highly recommend MSI computers. They're really great. That's what I'm using now for this talk. And then what you're running, I'm running Fire Capture. I like Fire Capture over Sharp Cap, and I'll explain why. And then you need Auto Stacker and Registax for aligning. So all this is free, that's free, and that's free. So the software is pretty much free. Okay, when you're preparing to go out, especially if you're gonna, this isn't as important like now Mars is up right after sunset. If it's clear out, just grab your scope and go, right? But before I was observing it for Alpo and in the morning, so it would be high up around 3 a.m. So I'd have to get up at 2 to observe at 3, 4, 5 a.m. So I want to see how the seeing and transparency is. So if the seeing and transparency are bad, don't bother, okay? So there's this program here called Astrospheric, okay? Kind of a nice play on words, atmospheric, astrospheric, see, instead of atmospheric, astrospheric. And then the clear sky clock, most people are familiar with this. And the whole idea here is the deeper blue it is, the better, okay? So notice here at 4 a.m. when I was observing on this day, see it was here above average, and then transparency average. So what is seeing and transparency? Transparency is how clear the sky is. What's the lowest magnitude star you can see? When you see like a deep, deep blue sky, no stars in the sky, that's like a transparency of like 8, 9, you know, that's like perfect transparency. That's your perfect deep sky night. Now the seeing is how turbulent the atmosphere is. So when you're looking at the planet through high power visually, you're seeing it move like this, or you're seeing it move like this. It's always moving a little bit, but it's better that it would moving slower than moving like this. It's moving scintillating very quickly, then you know you have bad seeing. See, in this white right here, if it were all white down here and here, you wouldn't bother, okay? That's very poor seeing, okay? So here was a night of good seeing, so I went out on that night and imaged, okay? So you get the idea of seeing and transparency. Transparency is the limiting magnitude, how clear the sky is, okay? And it's kind of an inverse relationship too when you're doing planetary. Usually when you're doing deep sky, you want perfect transparency. You don't want any clouds or haze or anything, because you know, you're looking at a 15th magnitude galaxy you're trying to image. You're not going to see if you got high cirrus clouds there, right? But for planetary, this blows my mind. If you have haze and high cirrus, it quiets the scintillation. It's actually better. The seeing is better when the transparency is not as good. So it's kind of an inverse relationship. Good transparency, you're gonna have poorer seeing. Bad transparency, you're gonna have better seeing. So when I look out and I see it's hazy, like in Florida, it's hazy and humid, and I'm like, oh, it's gonna be a good night for imaging. But for deep sky, forget it. So it's kind of interesting. And then another thing you want to look at is the jet stream. So you can go to this website, the Weather Underground, and the weather's going underground. That cracks me up. But here, so what is the jet stream? It's where boundaries where two adjacent air masses with different temperatures meet. And you can just imagine when you have two different air temperatures, you're going to get a lot of scintillation, a lot of turbulence. And here it shows it miles per hour, see 100 miles per hour up to 200, seeing the red and the blue, so the different colors. So you don't want a jet stream above you. And the nice thing about the jet stream is it always moves. So this is not fixed. So don't worry, if you wait about 3 days, this will be gone. So sometimes it comes over Florida like that, and you know, you just wait, and then once it's gone, you're okay. And I've actually imaged when the jet stream was above me, but it was in this light blue, and the seeing wasn't bad. The seeing was actually average, at least. So it didn't disrupt it that bad, but I bet if it was in the red here, it would really be bad. So look at the jet stream. So before you go out, check Astrospheric, Clear Sky Clock, and the jet stream to see how your weather conditions are. Okay, another thing you can use is what's called an ADC, atmospheric diffraction corrector. And this, I've gotten better in learning how to use this, but it's pretty much, I'm not too impressed with. It's about $150. Save your money. Put the money toward a good filter or a camera. But the way this works is you put these two levers together. There's two pieces of two prisms, glass prisms, and you turn them. Okay, and what's this supposed to do is, see here you have no correction, and this is with only with a color, and then see how it's dispersion corrected. See, so this would be Venus. Venus does this a lot, okay, because it's low in the sky. But notice here with Jupiter, the higher in the sky it is, you really don't need this. It's not going to do any good. I did an experiment. I used the ABC when Mars was really high, and I used it without it, and couldn't tell the difference after I processed the image or when I aligned and stacked them. So when the planets are high, you don't need to bother. So Saturn is usually lower. See, no, and then some. Damien Peach in the UK swears by it. He loves it, but I'm not too impressed with it. So unless you have extra mad money, get it. But the $150 is best spent on a better camera. Okay, and this is a great program called WinJupos. Okay, and this program is easy to use and difficult to use. It has a significant learning curve if you're going to do what's called derotating an image and doing measurements on the planets and stuff. But if you're just going to use this in ephemeris, it's very, very easy to use. And if you remember during the first time, I said I was trying to explain the difference between universal and local time. And I said, at first, there was only universal time here. And I said here, 0 hours universal time is 7 p.m. Eastern time now, the day before Thursday. So this would actually be the 7th. So if you try observing this on Friday, on the 18th of November, you missed it. You got to observe it on the 17th of November at 7:13 p.m. in order to see it. And remember, I said, wouldn't it be good if we had the local time up here? So I emailed Grisha Hunt. This was the club where I got the idea. I emailed the creator and I asked him, could you put the local time on there because it's confusing, I told him I live in New York time zone, all that. And he said, good idea. And he did it. And he even emailed me back, Greg, it's done. Check it out. So I think he was psyched too. Isn't that cool? So now it's here. So now we know our local time. But notice the local time is Thursday, November 17th at 7 p.m. Well, 12 plus 7 is 19. So it's 24-hour time. So
and we are forever grateful, Greg.
Yeah. I'm just glad I can contribute, And then here, on Friday, but in universal time, it's the 18th, 0 hours 13. You always state everything in universal time. Your local time doesn't matter, okay? Because there's people in China and in Africa and stuff imaging, and their local time is 24 hours different from ours. See, so but in universal time, it standardizes everything. So that's what's good about this program. So kind of check out, and it'll show you what the face of all the planets look like, okay? Jupiter, Venus, Mars. It's a fantastic program. Free, too. Okay, so here's the camera. Here's how the ZWO looks like, okay? And they come in color and monochrome. Now, if you're gonna get super serious about this, you get the monochrome, and then you buy a filter set, which is luminance, and then red, green, and blue. And then, then you combine them all, but I don't bother doing that. The color cameras now have become so advanced, even Chris Go was saying, a lot of them were saying on the tutorials that it's impressive how good the one-shot color planetary images are coming than doing it, red, green, and blue and luminance combined. So save a lot of time and just, start with the one-shot color. These get very fast frame rates, 2 megapixels. Another thing to look at when you buy this is look at the pixel micron size. Here it's 2.9, okay? If you look at a lot of the, you want a smaller pixel size, because what happens is the smaller the pixel size, the larger your image will be in your camera here. The larger the pixel size will be. And now the one I took the conjunction of Mars and the moon with was the 178 mm, which is 6 megapixel, and that's a 2.4 micron. And when I image Jupiter or Mars, I have to reduce the size by 10% to make it the same size as the 2.9 micron. So it's 10% larger size. Isn't that incredible? It's several millimeters more. And when you, multiply it by pi r squared, you get a larger circumference. So that's good without needing an extra balo or a larger aperture telescope, etc. Just the size of the pixel. Just the size of the pixels of the camera make it larger. Isn't that great? Now with deep sky, they're usually about 5.6 microns. They're like double this because you want larger pixel size because you want light buckets. You want each pixel to gather more light. Here, these Mars is at minus 1.8 now. Jupiter's at minus 2.5. I mean, these planets are very, very bright. So you don't need larger pixel sizes. So that's a good thing. And then balance. Oh, what the? Get out of here. Okay. And then balance the histogram here. I'll talk more about that. And then the file side, the file name must include the date and time in universal time. Okay. And then ZWO gives its own proprietary ASI capture software that you can use. I don't use that. SharpCap is another one. I don't use that one. This is the one I use. This is the one a lot of people prefer. Is this one called Fire Capture. And this is totally free. And I've emailed the creator to Torsten Edman, and he's in Germany. And I emailed everybody. And I asked him some questions sometimes. And, like in one of these beta versions, he forgot to add the planet Mercury. It didn't show up. So then he said, oops. So he added it in the next version. So now it's 2.7.10 is the official version now. So this is the way this works. It's very, very easy. You just type in here whatever planet you have. Jupiter here. Here he's using a red filter, so he's doing the red, green, and blue thing. This is a better format to use, as SCR rather than AVI. And with the SCR, you can go 16 bits, which gives you a lot more color depth. So I'm starting to use this more now. And then what you do is you adjust the gain and exposure so that these are as balanced as you can, the red, green, and blue channels here. And then you make sure this debayer is on, because that gives you the color. And then you make it, and it actually have a much larger field of view. You make it as small as you can. And this is the frames per second, you're getting 83. I'm getting more like 160. And then you press this button here and it makes a recording. And it's that simple. And I have a video of this. Time later, I'll show you how I go about in real time fire capture, actually catching the video. And then there's this thing right here where you can attach, where it actually has a tracking mechanism, where it actually auto guide this for a short period of time. So, and if a gust of wind comes, it doesn't matter. It still auto guides it, and it doesn't move like that. And I found out from someone that SharpCap does not have that feature. A friend of mine uses SharpCap, and he says, no, it doesn't have that feature. So I really like it for that. Who's Richard's iPad? Okay, so auto stacker. So this is auto stacker, which is really, really easy. Once you have the video, all you do is you open the video, shows up here, and then you hit planet or surface. If you're using the moon or sun, it's surface. Use the defaults, hit analyze, and it gives you this quality graph. And what this did is it organized all the frames, because all a video is 30 frames per second. And so here you have 9,014 frames. Now a webcam could never have captured that many frames, okay? So I have 9,000, almost 10,000 frames here. And what this did is it took the best one here and the worst one here. And what you want to do is right about the 50% mark, and you stack anything above this line and discard anything below this line. So usually about 50%. So you'll maybe do about 4,500, 5,000. Now, if you have bad seeing, go a quarter and stack only like 3,000. And then don't use two, this is a bad example here. There's way too many alignment points here. Try to use fewer alignment points because you don't need as many. Okay, they'll actually introduce artifacts if you have to. And then you hit stack, and that's it. It's that simple. And then it opens it up in this program called Registax, and then Registax has them. Now Registax will align and stack your images too. Before AutoStacker existed in the early 2000s, Registax was what everyone used, but now AutoStacker is far superior to Registax in aligning and stacking. But Registax has not been updated since 2011, and this was done through people through the Netherlands. And so here, you push these wavelets here and it sharpens everything. And this becomes sharp. And then you're basically done. You're like 90% done once you do that. You could do some more cosmetic things in Astra Image and Photoshop. And then here's Astra Image. But what I like here is has nice deconvolution, which is sharpening, has more wavelets here. And I like this micro contrast feature. And then this one I don't use as much anymore, the PIP, Planetary Image Processor. This will combine a lot of your video. It won't work for SCR. I found that out the hard way. So you got to use AVI for this video. You can attach all of these and you can make an animation. So you can take all these TIFF files and create an animation. It's great for that. Or you can join all your videos, see AVIs, and make one super video and all that. So, all right. And save your, another thing too is save your videos, because you can go back later when the software increases in software. I think, so here's my original one, 2003. And then when AutoStacker came out, Registax 6 rather than Registax 3, got some better resolution out of it. So save them if you can. I have a 12 terabyte hard drive, which I filled up. So now I just bought for Christmas 2 16 terabyte hard drive. I have one in a spare, so that in case one malfunctions. So I'm a digital hoarder. I save all my videos and images and stuff. So, but it's just one little black box. That's it. It's not like the movie hoarder, the TV show hoarders. It's just one little black box with all your stuff. So seen in a different light. This I just discovered during the great COVID shutdown of 2020. A friend of mine, Dr. Alberto Sequez from Tampa, was imaging Venus, and you can actually see the clouds of Venus with a violet filter and a UV IR cut filter. And so I was trying to do that. He was getting some success, but I wasn't. And then we were trying to buy a UV filter, and they were like 200, 300 bucks. And so I looked around and I found this for only $77. So for 25 bucks each, you can get an ultraviolet, methane, and infrared. So I would highly recommend buying this for $77. Okay, and if you and when you upgrade, I've upgraded. This is $275. The methane, that's $275, and the infrared's $100. So they're expensive if you get the upper end filters. But start with this; it gives really good results. And another thing to know is. See, the IR pass starts at 685 and goes to 1,000. The UV is from 320 to 380 and peaks at 350. And the methane is a narrow band. It's 890 plus or minus 10. nanometers. So when you look at, here's the cameras here, okay? Now, look at the quantum efficiency of the cameras, how sensitive they are to red, green, and blue light, but especially the infrared, okay? Because what ends up happening is 400 to 700 is visible. So from here to here is visible, 400 to 700. After 700 is all the infrared. And notice this camera at about 825, look at that, is 95% visible in the infrared. Then at 1,000 is 40%. Now the original one that I got, 290 mm, this only went up like here. This only went up to about 60% in its peak, whereas here it's going up to 95%. See, so this camera is the most infrared sensitive camera, which is really good. Oh, and there's a little protective window. You can unscrew this. It's kind of a picture here. See, this part right here unscrews, and then this part here unscrews, and you can take that little protective window off, but your CMOS chip is going to get dustier. And then this is a black and white. This is a 6 megapixel that's black and white. And this I use for, you know, the moon and the disk of the sun in H alpha. And that's why I bought it. But then notice this has terrible infrared sensitivity. Look at this, at 800, you're at 20%, whereas here at 800, you're at 90%. See the difference? So I don't use this camera to image in the infrared, but notice something else. It's very sensitive in the ultraviolet at 400, which is the start of the ultraviolet. It's 70. Here, it's not even showing it. It's like 45. See, so this is like double. And then it goes to, and then 380, which is what you want peak, is at 60%. And then 320s down here. So you got a lot of nice window, a very nice window here between 300 and 400 in the infrared. And that's important because the clouds of Venus are actually visible in the infrared, I mean, in the ultraviolet. So I'll show you images of that later. So look at your camera's sensitivity, especially in the infrared and in the ultraviolet. Usually they'll all be pretty sensitive in, you know, red, green, and blue. Okay, visible. And then here I'll just showing off a little bit some of my images. You can see Mercury here. This is my first images of Mercury. And here's a little thing I learned. Take long exposures of Mercury because Mercury doesn't rotate much. It takes like 20 minutes with the rotate 0.1 degrees. So you don't have to worry about it. And so 300, so take a long 5-minute video and align and stack only the top 10 to 15% because you have a lot of scintillation in Mercury. That's why you want to use infrared. One good thing about infrared is infrared light is not as sensitive to atmospheric scintillation as visible. So a lot of times if you want to image the moon, what you'd want to use is a 610, which includes all the red, but then all the from 610 to 1,000. So you get all the infrared too. And so it quiets the moon. So instead of using a luminance UV-IR cut filter, use an infrared filter. That's a little secret people use, and it's much quieter. And so you're able to get a much better image. And then this was published in Alpo's Strolling Astronomer. This is my image here. And then this is the image from Messenger spacecraft from Winjupos, and Frank Mielo, which is the coordinator here, identified features. Look at that, you can see features. I actually imaged features on Mercury. Do you know how hard that is? This was my original one. You're not seeing any features here, but I mean, look at that. And this was on the 4th of July this year, on the morning of the 4th. So I got up really early in the morning for this. Notice the altitude was 26 degrees. It was daylight out. Okay, so Venus, when you look at Venus in the visible or in the infrared, it looks very vanilla and nothing exciting. But look at this. When you look at it in the ultraviolet, see these dark bands here? Those are the clouds of Venus, and they're dark because they emit. The clouds contain sulfur dioxide, and they emit ultraviolet light. The filter absorbs ultraviolet light, so the ultraviolet light never reaches a CMOS chip, so it appears dark because that's where the cloud is. We think of clouds as white being on Earth, right? But it's the opposite on Venus because they're emitting ultraviolet light, and your filter is filtering out ultraviolet light. So the UV light never reaches the CMOS chip, so it appears dark. Isn't that beautiful? Look at that. And this was done with the cheap filter too. So you get really good results with the Astromania filters. Okay, and then here's Mars. This was from 2020. Here's in red, green, and blue. Here's Syrtis Major. See, India here. And then here it is in the infrared. And then Jupiter. One nice thing I love about Jupiter, what are called shadow transits. You can just go fast forward when Jupos, and these happen all the time. But if you see them in your location, is different. But this is the moon Europa, and this is the shadow of Europa being cast on the disk of Jupiter. Jupiter is a gas giant. There's no surface. These are all clouds. Isn't that cool? And you can actually see it move across. It takes about 2.5 hours, depending where it is here. But you see these shadow transits, and I love shadow transits. I try to never miss a shadow transit. And here's how it looks in the infrared, okay? And then here's how it looks in the ultraviolet. But notice how it looks like in the methane band. Isn't that exotic? That does not look like Jupiter that we know and love, does it? That looks alien. I mean, look at it. And what you're seeing here is in the methane band, which is 890 plus or minus 10. Now the better filter is 889 plus or minus 18. That's in a little more. But what you're seeing here is more methane, darker and lower, no methane, brighter and higher. You're looking at clouds. So if there's no methane, they're darker, the clouds are lower and they appear darker. So these have more methane here. Okay, if there's no methane, they're brighter and higher. So the equatorial belt here is devoid of methane relative to this other parts of Jupiter. Isn't that cool? And then look at this image. And then recently we had the Webb telescope, the image did at 2,120 nanometers, and I'm imaging it at 889 nanometers. Look at that. Looks the same. Isn't that cool? I mean, look at the resolution I'm getting. You're never going to get what the Webb's getting, but I mean, look at that. You can see the same thing. Isn't that cool? I love this. And there's another shadow transit. It's not the same one, but it's really amazing. And then here's Saturn here. And then that's in color, that's in infrared. And notice when you use the methane, the Jovian methane filter, 889 nanometers, Saturn disappears. Isn't that amazing? It's absorbing all the methane from Saturn. And so it appears dark. And since the rings are made of icy, rocky, icy particles, they don't have methane, so they appear bright. And then here's Saturn. Notice the ring tilt. Now Saturn is moving, so the rings are going to be like face on. They're going to disappear. They're going to be aligned in another year or two. And this was amazing because this was only 2 days after Category 4 Hurricane Ian hit, September 30. And I was pretty close to that, unfortunately. And look how nice. It's one of my best images of Saturn. Isn't that beautiful? And then I imaged Uranus. Here it is in color. And this is the polar region here. Here's Neptune. You can see the same thing. And then this was all done in one night. On October 11, 2020, you can see all the planets except for Mercury, which wasn't out. Pluto's not a planet anymore. And so 0 hours. So that's 7 p.m. Oh, that's 8 p.m. because we didn't turn the clocks back yet. So that's 8 p.m. and then 8:54 and then 9 and then 11 and then 12:30. And then this was actually the next day, just before sunrise, but it's the same day in universal time, 11 hours, and that's all that matters. And now look at this and look at it in infrared. Isn't that cool? And that's ultraviolet. These are infrared. Notice, isn't that cool? You can see a little more detail here in the infrared with Jupiter. And then in the ultraviolet, look at the clouds. I love the cloud features of Venus because they're always changing and you can't predict them. So it's really valuable to take images in the UV of Venus and submit them to ALCO. And then lunar imaging. Here's the lunar X and lunar V. Oh, does anyone know where I could get a table of the next lunar X and V sightings for 2023 each month? Does anyone know? Have a site, put it in the if you know.
Sorry, I
And
don't
then-
have them off the top of my head, but should be able to find it.
I think you
Okay.
could just Google it.
Yeah.
Yeah, that's
usually.
pretty much where I got it from.
You
Yep.
just I tried Googling it. I didn't have much luck, but and then this was another one you could focus in nice and close. Rectus Rupra. This is the straight wall on the moon. And it's funny, when I first imaged it, usually I image the moon like the whole moon, and I saw all these little spots here, and I thought those were artifacts. And I'm like, God damn, I'm getting artifacts. So I looked at Virtual Moon Atlas and I blew it up to this scale. Those aren't artifacts. Those are real. All these little tiny craters here are real. It kind of surprised me initially. I'm like, wow, look at the resolution I'm getting. You know, it's amazing. I mean, everyone should be jumping up for joy seeing this. That you can do this for what, $300? You know, for just a few $100. You already have your scope. You know, and then here's the lunar eclipse, May 16th. I took that with the 462 one-shot color. This was during total. Look at the shadow of the Earth. And then solar imaging, white light and hydrogen alpha. So here's the white light. And then notice this is just about 20 minutes later. So this is the exact same day. You can see here's the, notice it, the sun looks so alien. This is the photosphere and that's the chromosphere. And you can see, notice the sunspots here. You can see those sunspots there. You can see these sunspots here. See that? So, and then these prominences that are like coming out at you rather than being edge on. But it's so beautiful. Look at that. That's the exact same sun 20 minutes later. So. And then amateur astronomers are approaching Hubble quality. This is one of the premier imagers, Chris Go. He lives in the Philippines. And here's his image of Jupiter. And here's the same image taken by the Hubble Space Telescope with a 96-inch mirror above the atmosphere. And here's a 14-inch telescope on Earth. Isn't that identical practically? I mean, look at that. See, so that's why these images are very, very important now, because with different observers being in different parts of the Earth, we can get a complete, and people are making Jupiter maps. I'm getting emails where they're getting a complete rotation of Jupiter from one end of the planet to the next. So it's really, really cool. And if something happens here, we see like a Shoemaker-Levy spot or something, you know, that can notify the professionals, and they'll turn the Hubble and the Webb on it and all the ground-based scopes. And so, you know, we'll make the discovery before they do, because we're out there actually looking at this stuff every night. So like I said, planetary features change frequently, and we can aid science and then submit them to these organizations here. And then these are the, like I mentioned, Chris Go, Damian Peach, he's big gun in the UK, and Don Parker he was in Coral Gables, Florida. He passed away in 2015. But see, notice the old technology, they're huge. That's the old S-Big cameras. Okay, so concluding remarks. So observing planets either through an eyepiece or digital is satisfying and rewarding experience. So purchase a video camera, use your telescope and notebook computer, start imaging the planets for yourself. All necessary software is free. Get this filter set so you're able to see planets in a different light, and then you can make important contributions to science. So what are you waiting for? Start imaging. And then this was this already happened. So, and that's it. Any questions? And let me show you, let me see.
Hey, Greg, it's Ernie. Thank you so much for your talk. I had missed my calendar notification, so I missed most of your presentation. I'm wondering, are the slides available to go back?
I already emailed them to everybody.
Oh, great. Thank you.
Yeah, on the group. Yeah. Yeah. So here's can everyone see this? You may not be able.
Yep.
Yeah.
Yep.
Okay, right.
Just about every time a group reminder went out, he sent a copy out.
Oh, share sound. Okay. All right. So here's how to go about using. Can everyone hear me?
Yes.
I'm narrating it. So here, first thing you want to do is focus. So you have this nice big thing here. 2 minutes. See, notice that's with the fine focuser. See how it's scintillating, how it's moving.
Yeah, Greg, you're using Barlow on there, right?
Yeah.
Yeah,
1.5.
yeah, you're using a 1.25 on everything. Is that what you're using?
No, I'm using a 1.5 on this, but now I'm using a 2. I can push it a little long. So so what am I saying now? All right, so first thing to do is focus it like this. See, this is not that great a night, because if you had a better night, it wouldn't be scintillating as this. This I would say is about average night. Maybe, see, so you do Mars, RGB, and then you have the STIR and the 16-bit. And then you want to balance the channels. See, and then adjust the gain and exposure. What I usually do is underexpose it, because if you have it perfect exposure, the light, when you align and stack, the lighter parts are going to get overexposed, I found. So if you underexpose it, you can always bring it up. See, so it's better to just underexpose it.
What do you use for gain?
This is actually
you just adjust it right up here.
I'm using a 2x Barlow.
Now here, this is the actual size 100. What I do is I go 50%. I find it's easier to focus on these albedo features at 50% than it is at 100. See that?
Mhm.
And when you take the video, it's going to be at 100. So even though you're seeing at 50, it's going to record it at see, it's much easier to focus on that being 50%, I find, than 100. See? So that's just my little trick I use for focusing. Okay. And then
You try to enlarge that image at all, which you can do with fire capture.
what do you mean?
Drag that.
Gain and exposure.
What do you mean enlarge?
Yeah, isn't there some way you can drag that top bar to make it just show bigger on the screen?
Yeah.
Do you ever
That's
do
what
that?
I did.
Is there any reason to do that?
See how I have it 100?
Yeah.
I could
oh, the
go
100.
200.
So you can go
I
bigger.
you just go like that. Yeah.
Right.
But if you go bigger, it doesn't really, these become a lot blurrier. The scintillation becomes,
Right.
you know what I mean? So that's why I like focusing at 50. See
50.
that those
Right.
look a lot sharper there to me than if I tried sharpening it at 100. See, that's just my little
Okay.
If you want to do it at 100, go right ahead, or 200. Yeah, it doesn't matter. This is just my little trick that I found works for me.
Yeah. Well, on the cameras, you're using the ZWO 290
Yeah,
and a
says
460 and a 462. Which one do you like better?
Oh, the 462.
Yeah.
Because it has the higher IR, has the higher IR sensitivity. And when you looked at that image of methane in Jupiter, what happens is the 290 did not have as much sensitivity in the IR. So you had to do what's called binning ×2, which made it half the size smaller. And then you had to unbin it when you did it because you could barely see it. With the 462, you don't have to bin. It's nice and bright. So that's a great thing about it, you know? So notice how you're changing the color channels here. See, now if you're going to
could you explain that, how you balance that histogram? I've been fooling with that without too much success.
Oh, okay. What you do is right here, for the ZWO cameras, first in the creator had in the old version 2.6 only red and blue, no green. Now he added the green channel for the ZWO camera. So what you do is you just move these until these are about equal. Now they're not always. See how sometimes they go a little forward, a little back, but basically they're equal. See here, I show where they're not equal. Like, see there, I pushed the red. I pushed the red. And see how it looks very red? See how it looks very red? So you don't want this histogram here because these two are balanced. So just push that back and see as I push the red channel back. Let's go.
So what's that, Greg? What's that blue line you're playing with at the bottom? I don't think I've seen that. Is that new?
What, this?
Yeah.
No. This is this is a video I made using my screen recorder. All right, which is available free. So that's just a video.
Okay.
And see, so and you can adjust. So just make sure these three are as close as possible because you do finer adjustment later. I'll show you in register. So that's it. So balance that, okay, and then here you can click on this. It shows you see 17.2 arc seconds, 1.8. I figured out the altitudes wrong, but I had to put a negative sign. So now it's correct. Here's a central meridian, shows you what your focal length, your F ratio is. It's a fantastic program. Now, notice here, when you're full frame here, you're only getting 50 or so frames per second. Now, what you do is click and hold down and make it small, and it jumped to 160, 170. See that? So you don't want to, when you do the final video, record the whole thing here. Your frame rate is slow. It's only 50. If you ROI region of interest, and they have preset ones here. There it is. Look at that. It jumped to 170.
Yeah, Greg, you were using a 9,000 frame video. Is that standard? Is that a good place to be?
Yeah. Oh, I can get even more than that. I've gotten up to like 20,000 frames and 60.
That takes up a lot of room.
Yeah. Oh, yeah. It's another thing I didn't mention. 4 gigabytes. Your average tends to be 4 gigabytes. If you do a surface like a full moon or the sun, it's usually 7, 8 gigabytes. I know. That's why I'm a digital hoarder. I have a 16 terabyte hard drive to put all this stuff in. Okay, to save it. Other people just delete it. Oh, here's the big thing that SharpCap does not have. you press this thing here and it actually tracks. You press, which one is it? I think it's that one. See it? So it has this alignment box and it actually tracks it now. See it? And then you hit, and then you just hit, and then you just hit record. And then this shows you here how many seconds, how many frames you got, and the total, and how many frames per second. So that's second, actual frames captured, and frames per second average. So I went all the way here. So, oh, I guess I went 90. Oh yeah, I'm going 90 seconds. You can go 90 seconds on Mars because it doesn't rotate much. It only rotates 0.3 degrees in 90 seconds. I timed it. Whereas Jupiter will rotate degrees and it rotates very quickly, and plus has 3 different central meridians. So look at this. So 90 seconds, I got 15,000 frames. Isn't that amazing? 15,000 frames. And that's basically it. Okay, and then let me show you how you would align and stack that really quick.
Are you tying it up now, Greg?
Yeah, I'm tying it up, but just
Thank you.
let me just show this because I think this is important. It doesn't take that long. Okay, open. So see how easy it is to capture it. The program is pretty intuitive, and there's a lot of YouTube videos on it. Okay, so let me see, share screen now. Is that open here and here? 3. Share. Okay, can you see all that?
Yep.
All right, good. I figured out how to share multiple ones. Just have to hit control and click on what you want. So RGB, so I opened it here. Now I hit analyze. Okay, notice how fast it's going because this is a fast MISI. I have another one. This is 8 cores, 16 threads, and it was upgraded to 64 gigs of RAM. Can you believe that? So this one has 7,124 frames, okay? So now this one is not a good night because this is falling down very quickly. If it's a good night, it tends to stay way up like this. So I'll stack a quarter, plus it takes longer if you stack more. So let's do 2,000 frames. This is the top 28%. Quality is 48, which is close to 50. So you don't want to stack here because quality is only 32. Even though you're stacking more inferior frames. So it's better to stack less frames that are better quality than more frames that aren't good. And then you have this, and then use this multi-scale. Now this drizzle takes a long time, but and then find the right. So here 14, that seems like a lot. 40, yeah, that's better. 10, let's see, 48, 5, no, that's too few. So I think 10 is a good amount. Okay, you don't want to have too many. And then you just hit stat and then go here and make sure it says open in registacks. Okay, and then just hit stack. And now now it goes through its whole, now it goes and it's telling you what it's doing: buffering, reference frame, alignment, stacking. Notice how fast it is. Oh, I have a fast computer, but now if you were to do drizzle, it'll take like 2-3 times this amount of time to do. Drizzle is just another algorithm. The Hubble Space Telescope uses that, and you get a little finer resolution with it. And then bang, done. See that? And there it is. And then here you go to RGB balance and hit that. See, so see, they were pretty well balanced, the channel. See, only a little bit. All right, and then you can align it better here like that. And then all you do, I have some presets here, but you just move these and look at that. Here's our snake. or worm. Isn't that cool? And there it is. And then you can try different. See, be careful not to, you can always over sharpen. That's always a problem. People want, oh, I can go sharper and sharper. See, look what happens if you try doing it too much. It actually doesn't look as good. So you want to be a little under sharpened than over. See, that looks a little too much. See, and plus you're getting things. So, but that's basically it. Then you save it, and then you can do more cosmetic stuff in Photoshop and all that. But that's basically it. It's that easy. I mean, how long would it take you to do deep sky? Taking 5-minute subs and red, green, and blue and luminance, and then combining them, the hours in Photoshop. This, I mean, 60 seconds to do the video, and then another 2-3 minutes, or like within 5 minutes, you could be totally done with that. That's all it took. 1 minute to capture the video, and I do a lot of this on the fly, so I can see, because I want to see this quality graph, how good it comes out. Because I'll stop, if I don't have a good quality graph, I'll take another. Once I get at least 2 or 3 really good quality graphs, then I'll stop and use another filter or go to another planet, So, any questions? That's basically it.